Okay, welcome everybody. How's it going? All right. Thanks for the thumbs up, I appreciate it. I'm grateful to have the opportunity to be here with you again. And today we have an opportunity to talk about axial loading. Okay, and some of you, I understand, have already done the assignment, which is great. And if you don't want to go on to the next assignment, it'd be wonderful if you help answer some questions for other people in the class. As the hands go up, please feel free to get there before I do, okay? As long as your classmates are, willing to accept that. And yesterday, it was great. There was a question in the group meet during office hours, and then someone walked in during office hours, and I didn't answer the question in the group meet because I was talking to the person in office hours. But then someone else, or someone, I should say, answered the question in the group meet. So I'm grateful that you are covering for each other. That's kind of the organic process that I'm excited about here. So in this session, okay, as you go through the problems and as you go through the material and the video, I hope we have an opportunity to think about bars, okay? What are some systems that you can think of that have bars in them? Yes. Okay, trusses, right? Two force members, right? And there was a question about some material to review, and we posted in the announcements and also on the session 2 page on engineering-content.com, right? Some of the sections from Hitler's book on statics. And so that's one of the things that was covered in there as well. So good. Two force members just meaning that there's a force at either end without a transverse load along it, and no moments at the ends. Okay, what are other structures that you can think of that have bars in them? Yes? Okay, so maybe the struts in a car, right? You said car suspension. Yeah, so one of the problems, right, was that of looking at, or is that of looking at a strut maybe on an airplane or something like that, and it has a bar, and there's a wheel underneath it for being able to allow the plane to land nicely on the wheels instead of slamming into the ground. Yeah. What other structures have bars in them? Yes. Buildings, okay. Yes. We have lots of bars or pieces of trusses often in buildings. Okay, yes? Yes. So are the spokes in the wheel, are they in tension or compression? Okay. Yeah, so like if it's loaded, right? When they're tightening, right, the spokes, they're attempting to put them all in tension, right? So that the whole thing is actually, it's working against itself, right? But yes, yeah, you want those to essentially be in tension. Great, good. The bars of a table, the legs of a table, right? Those are bars, right? So like when I was an undergrad, I got excited when I was taking dynamics, and I would go to the table we were sitting at, and I twist it, and I watch it go back and forth, and that's a mass spring damper system, right? So you can kind of begin to think of the objects and the structures around you in terms of structures, or in terms of dynamic structures, or in terms of static structures. Okay? So bars are obviously very relevant to the world around us and the design that we do. It turns out that bars are also a nice shape, shall we say, for doing material testing. So when we cover material testing in session 5, I think it is. Okay, so not the next one, but the one after. We'll talk about bars. We'll talk about how we test them. And it's the easiest of the structures that we cover in this class to calculate stress. okay, within the bar, or strain within the bar, right? So, and that will be on Thursday when we cover that. Okay, but for today, all right, what we're going to do is we're going to say, we're still not talking about the properties of the material. We're talking about the properties of a structure. Okay, so when someone gives you a stiffness, that is not a material property. That is a structural property. Okay, it's like they hand you the spring and they say it has a coefficient or has a spring constant, all right, of whatever. Okay, something newtons per meter. Right, that's a structural property. Okay, a material property, which we'll cover very soon, next week, refers to if I gave you some mass of this particular material, okay, you would be able to say, it has a density of this, right? Density is a material property that we're already familiar with, right? The mass of whatever that glob that would be a structural property because that's the integration, right, or the agglomeration of all those material elements, okay? So it's important to be able to distinguish between the two, okay? What's a material property and what's a structural property? So today we're primarily dealing with structures because we're given a spring constant, okay? Now, there are multiple ways to go about solving for displacements and forces. Okay? The general approach for forces up to this point in your studies through statics and whatnot is to first take a look at what the equilibrium is externally, right? And then use method of sections, most likely, unless it's a truss and you want to use method of joints, okay? But usually we use method of sections, and that's when we do the cutting. And we spend a lot of time, right, talking about what the conventions are when you take a cut. If it's a beam, if it's a bar, if it's a shaft, okay? Or truss, right? You can take a slice there as well. So with those techniques in statics, we're able to often calculate the forces and the internal forces, the external forces and the internal forces. But sometimes these structures have an extra constraint, okay? So let's talk about this for a second. Here is an object, all right, which is a bar, okay? And we're going to think about this also in terms of being a beam in a second, okay? If I were to magically balance this on my finger, I can't do it, all right? Right, I would have equilibrium. I have one contact, all right, at the bottom working against gravity, force of gravity acting on this object, right? And that's pretty straightforward. And you're like, okay, I understand what's going on, right? And if I have this bar and I pull from both ends, okay, and I'm not applying a moment, right? Again, I can figure out, okay, the force of this hand on the object and the force of this hand on the object, they're equal and opposite. I'm in equilibrium, okay, and I'm happy, right? Now, what happens, right, if I clamp both ends, okay, and then I don't know what's going to appear if I flick there, right? Something personal could. But anyway, and then I apply a force with this forefinger there, right? And imagine it's external. So let's say like this plug is able to apply that extra load, okay? Are the forces by my hands, when I have that extra load, pushing up or down here, are the forces at the top and bottom by my hands acting on this bar the same? No, right? No. But I can calculate external equilibrium, or can I? Right? We get into an interesting situation. where if this is perfectly constrained, okay, and I have another load here, then as someone put in the GroupMe, I have to know something about the squishiness of the top portion above my finger and the bottom portion below my finger. Okay? And this is when statics by itself is not a sufficient tool. Okay? Or equilibrium, better said. Statics, sure, everything's not moving, so that's okay. But when force equilibrium by itself is not a sufficient tool to be able to calculate the forces. And this is because the system is over-constrained, all right? And I have essentially to take into account the material property, the structural properties, okay, of this configuration to be able to solve for equilibrium. And to be able to solve for, well, how much does my middle finger move up, okay, as I'm pushing on it. So there are multiple ways to tackle these indeterminate problems. Another, probably simpler to visualize indeterminate problem is the following. I have a beam, okay? And if I clamp one end of the beam, now I have gravity acting over here downward. This beam is statically determinate. Why? Because my clamping on this side is providing both a normal upward force and is providing a reaction moment, right? It's counteracting. So this nice clamp over here is providing two constraints, okay, to keep this thing statically in place. If I had just a pin, right? You guys remember the pins from statics? What happens? Whoop! All right? That falls straight down. All right? That becomes a dynamic problem. Okay? So I need these two constraints. Now, what if I just add a force here? Or a constraint, better said. A constraint. Okay, now I've got gravity and I've got a constraint on this side. I've added one extra constraint, which makes this system over-constrained. And so I can, like, you can do it with your own cell phone right now, right? The thing cannot move at all, right? Nothing's moving, but I'm like, I can crank up the forces. I can crank up this force, I can crank up this force, I can crank that moment. I can crank up the loads. But everything's static, right? But so how can I calculate things, right? I'm at a loss, okay? So again, we need to know something about the deflection of the object, all right? We need to know something about the squishiness of the beam, okay, in terms of what the person in the GroupMe put, okay? All right, in order to be able to solve for the forces and displacements. And you're just like, well, there's no displacement. Well, there's no displacement at the ends, right? And this makes it even more constrained. If I do clamp, right, that's like now two extra constraints that I don't really need, okay? But they provide some stability and they provide extra support, but they also make my life more complicated, okay, from the perspective of doing the calculations. But there's deflection. You can't really see it, but there's deflection in the middle. Okay? There's deflection in the middle. So the profile is going to be dependent on what I've got at the ends. So with indeterminate axial loading of bars, what you'll see is that we can use geometric compatibility, which is how Hibbeler normally approaches it. Well, actually, no. Hibbeler does both of these. I shouldn't say that. Hibbeler emphasizes both of these techniques, superposition and geometric compatibility. We're going to focus a little bit, we're also going to talk about it here, but we're treating these members as springs, and we already know how to make a network of springs into some type of equivalent stiffness, okay, which allows us to kind of simplify things and not have to look at the forces and the geometric nature of the problem, which you'll see if you look in Hibbeler's book, it can get a little bit confusing. Not because I think Hibbeler does a great job on it, I just think that this is a simpler approach when you start to think about bars as springs. Now, there are other complexities that we can talk about here as well. When you do these structures, all right, we can assume that everything is rigid, okay, and that nothing is rotating, which is nice. Okay? But in reality, things can rotate just a little bit. And when they do, when they start to rotate, we have to think about the angle of rotation and how that affects the forces that we have, and how that rotation, how those displacements affect the forces that we have in the springs that we're using. Okay, so that's pretty much the introduction for now. I understand there are some questions. So Praj, are you? Yes. So Praj and I will go around. We'll try to answer field questions that are specific, and then occasionally I come up and I'll try to map it out for everyone. Are there general questions though before we get into that part of today? Are there any general questions or conceptual questions that you would like to kind of discuss as a class? Okay, well, I'm sure we'll get into it. Okay? So we'll go ahead. And we'll also do the attendance. All right. All right, good. Yeah, take pictures of yourself, right? Wrong button. Okay, I'm working with people who have questions. Who has questions right now? Okay, you guys have questions? Okay, so could a couple people who have done the assignments take a look and walk over and talk to some of these people while I'm walking around too? And then Praj is also walking around? Okay? Because I know you're in here. So keep your hand up for a second and they'll come and they'll find you. I hope, if they can. Okay. So in that case, so that's the relationship on one. We have
Oh. You're just weird. Yes. I promise
Yo, I have to write this. I have to write this. You are not helping. I'm not even. What should we do?
Was this notation like okay, was that just aesthetic? She was or is it regular? I couldn't find her. So that's what's right.
Try that. That will help.
Sorry.
Other question. Other question. Okay. Clear this.
Better go. I'm just as soon as his bag is off, I got the key. Okay, maybe you actually have the time. I'm gonna go pee. It's correct. So.
Not before you have then it's over. They displace, they go on the right, they not. What are the forces you want? That's right. That's right. So whenever you open up a series, let me ask you a question. Probably before this is not just trying to so the force is more. And you can do that. So both of those, so they're because it's by this. It's the switch. Right? Or one of the and Apple uses what if you put constant and then let's say. Okay, so there are two ways to do this. One is to do external equilibrium, right? And figure out what the reaction goes from the wall on the structure is. And then slice and just look at the reaction. The other way is to slice that green and then say, okay, that's a piece from now. Okay, we're getting to the. Yeah. Alright, so I see, like, I'm looking at this, and I see, okay, these are parallel, and I know that these are parallel. Or is it parallel? Well, they have, but in general, you have two things in parallel, A1 and A2. Now, it's a street. Right, so, look, A1 and A2, right? This is still there, that's still there, that's still there. So then, now I see this system, and I'm like,
Okay, so it's just, okay,
now let's go back and go back to that.
just say this, so it's okay.
So, if you go through, right, so there's an one over or like one over effectively it's just another one. No. You have to do one over K1. But this one is just. So this is K1. So 2K1 squared over 2K1 plus K1. So it's going to be 2K squared divided by. Yeah, and then now we got that one. Okay. We got that one. Then you overcome parallel. We have the three other ones. We're going to do one more. Got it. Yes. It doesn't really matter. You just have to be very Yes, it is. Of course it matters. Yes. How you write it, it's fine. So, yeah, so the signs mean the sign is negative. Right, so, yes, it is, right? But I'm adding these relative to space to be covered. And I have to keep it overall. Okay. More questions?
Still, it comes forward here. Yeah, no, this is the
Okay.
second, the first approach. And then,
The first approach means you outside of,
yeah, so here, that's
okay, so we have,
and then I realized arms.
hold on, where does that come from? Okay, that's fine. R1 equals to A1.
That's why.
Okay, so there's R1. Okay. Okay.
Here, so it's.
Okay, so that's where it's,
I mean, I did too.
okay, and you're saying this is. Oh, because. Well, there's something goes back to here. Doesn't it? Something, yeah, it's goes back all the way here. F is equal to R1 plus R2. That's what's in here. That's right in here. That's not. That's right. F is equal to R1 plus R2. That's not what we have here. Okay. Other questions? Questions? let's talk about this one. This one's now come up.
Okay. So, I've talked to some of you about this problem already, and I think if you're doing something else, it's fine. All right, no worries here. But if you want to tune in, great. Okay, so we have a system where there are 3 separate stiffnesses of bars in series with each other. Okay. And there's a F1 applied here at this interface, an F2 applied at this interface, and an F3 applied at the right end. Okay? And the question is, what is the overall delta? Okay? Now, there are a couple ways to approach this problem, at least 2. All right? For now, let's do superposition. Okay? So what does superposition mean in this case? Superposition means that I am going to look at the response of the system to each of these forces individually, and then once I have those responses due to the individual forces, I'm going to add those responses up to each other. Okay? Oh. Isha. Okay, now I know. I didn't recognize you. Okay, now I was like, okay, one context and another. I was like, oh, now I know who you are. Okay, absolutely. Okay, so sorry. So what are we going to do here? We're going to say that this system is equal to the following. We're going to say, what is the response okay, just due to F1. So F2 and F3 are 0. Okay? Then we're going to say, we're going to add this up, and we're going to look at the response. Just to F2. Okay? And we're going to look at the response. okay, just due to F3. Okay? And this is using superposition. So it's important to keep in mind that what we need to do is look at the response at the right end. Okay, we're adding these responses up to these individual forces, F1, F2, and F3. Okay? So in this sense, right, we need to figure out what delta 1 is, delta 2 is, what delta 3 is. Okay? And so how do we do that? Well, what are the forces in these second and third members over here? These forces are 0. Okay? Why is that? If I take a slice here and I were to open, like if I took a slice here, I don't know why I did that. Okay, if I took a slice here, there's no force on the right end, so there can be no internal force on this end, right? This is a 0, this is a 0, right? And similarly, if I do that here, that's a 0, that's a 0. So what I say is that these two are just along for the ride. They displace, but they do not deform. Okay? This one, on the other hand, all right, this definitely has an internal force. And that internal force is because of F1, okay? And there's a reaction force here because it's got to be static from the constraint. And so if I know what the internal force is and I know what the spring constant is, I can figure out how much the displacement is. And these are along from the right, so I can also say that that delta 1 is equal to that delta 1. Okay? So what do? I say F1, I'll do it in green for fun. F1 is equal to K1 delta 1. Okay? And so then delta 1 is just equal to F1 over K1. In this case, all right, I have some delta 2 I'm interested in. This member is going along for the ride, but F2 is going to be acting on both of these members. And these are springs in series. So I can think of this as, oops, two springs in series, right? I have a K1 and I have a K2, all right? And I've got the force acting on them like this, F2, right? And in this case, the displacement at this location is equal to the displacement at this location, right? And what's happening is that this displacement, or this force, sorry, is actually in the opposite direction as this delta 2. So this equation, all right, so I need to figure out what the equivalent spring, so I need to figure out what the equivalent spring is. Okay, so that equivalent spring, that K equivalent is going to be equal to, well, I can do it a couple of ways. I can do it this way, or I can just use the expression that we commonly have for two springs in series as the following. Okay, so the delta 2 in this case is going to be actually minus F2, okay, over K equivalent, okay, which is minus F2 K1 plus K2 over K1 K2, like that. Okay. And you see where this is going. We have delta 3 that we had to calculate, we have F3, we have 3 springs in series. So if I think of the purple, okay, we'll call it 1 over K equivalent 3. Okay, maybe I should have called that 1 over K equivalent 2. That's going to be 1 over K1 plus 1 over K2 plus 1 over K3. And delta 3, oh, I use a different color. Delta 3, okay, is going to be equal to F3 over K equivalent 3. All right, and if I take the holistic picture, delta is equal to delta 1 plus delta 2 plus delta 3. All right, any questions on that? This problem is nice because it demonstrates how we can break these systems into simpler springs or simpler bars, okay, by combining or coming up with equivalent spring constants for these springs in series with each other. Okay? And that seemed to be, this seemed to be a question that multiple people had. Yes? Okay. Are there other questions? Yeah. Okay, so because there's a difference between displacement and deformation. Okay, displacement is right. If you know, how can I describe this? You know. Sometimes they're the same, sometimes they're not. They're not, okay? Sometimes they're the same, sometimes they're not. But when we're talking about deformation, we're like, how much is this particular region stretching or shrinking, okay? Whereas, depending on what happened next to it, right? So like displacement, like if I pull my arm like this, right? I've got this stretching, I've got this stretching, I've got my finger stretching. Right? And then I'm looking at the end point. Okay? If I look at the deformation of the middle, let's say this region is in the middle, right? It's displaced, this end of that region has displaced a little bit this direction already. So if I'm looking at just the deformation, how much this has changed its length, it's not how far this has moved, how far my wrist has moved, right? But it's how far my wrist has moved relative to the interface that has also moved. Okay, and so the change in length, that's deformation. But if I look at displacement of my wrist, that also has some stretch from the first, from my, what is this called? What is this called? This is forearm, this is bicep, I guess, of my bicep. Okay. So that's the difference. So now the question is, how do I figure out the deformation in the second region, right? That's what you all are asking, okay? So how do you do that? Well, this is maybe a subtle point. Deformation is dependent on internal force, okay? So yes, we often think of reaction and action pairs, okay? And we think, oh, I'm pulling by this amount, all right? And there's no reaction down there, okay? And so I know I'm stretching it by that. In reality, what we care about is what is the internal force, all right? And if its internal force is constant across it, then that's what we use for the deformation of that member. Okay, it just so happens that that internal force is often equal to the external forces that are being applied. Okay. So in this case, what we need to do is, so now let's just, which question is this? I don't know. 4? No. Yes, it's 4. Okay, it's question 4, all right? Let's make it simpler for ourselves though. Okay? Yeah, so how much it stretches is what we're interested in. So in order to do that, we had to take a slice. We had to take a slice there and figure out what the internal force is. Right? So there are two options. The easier option, I think, is take the slice okay? And we want to balance, so we use our nomenclature, right? Our
Why is it easier?
internal force, okay? We use our convention, right, where we have it coming out.
Why is
Of
it
the-
easier when you want this piece of the
Oh, why is it easier? Because if you do it from this side, I had to figure out what the reaction force of the wall is on this system. So first I had to do external equilibrium, which is fine, all right, but I'm just trying to skip a step. Okay, so in this case, I have, if I call F2i positive, I have F2i plus F2 minus F3 equal to 0. So F2i is equal to F3 minus F2. Right? So this is the internal force. This is the internal force. And so, or, whoa, do I lose? Okay, whoa, that's weird. Okay, so this is the internal force. So if I know that internal force, and if it's coming out of the face, it's in tension, right? So if it's positive and coming out of the face, it's in tension. If it's this direction and it's negative, then it's in compression, all right? And it would be negative. Honestly, I don't remember which one I programmed it to be, okay? But the deformation, all right? So the deformation, we'll call it deformation of the second member, is just going to be this F2i divided by K2. All right? That's what the deformation wound up being. And
because I don't care about the deformation. F3.
correct, you don't care about the deformation. Yes, that's well said, Daniel. Okay, because we're just asking what is the change in length of that middle section. All right, and it really, in this problem, it really doesn't matter what the K3 is here. Okay, because this is in series with this region here. Okay, so I could have K3 as long as it doesn't break. K3 could be whatever I want, but because these are, if they're in series with each other, and this is a statically determinate system, it could stretch a whole lot, but the force is still going to be the same, acting on this member. Okay. Good. I'm glad you brought that up. Yeah, these problems are designed to kind of make ourselves ask questions, right? About what does it mean to satisfy equilibrium? Okay. And if we think about internal, this is, we're not talking about stresses yet, but we will very soon on Thursday, okay? Stresses are really internal, okay? And they are dependent on internal forces over areas, okay? Great. Question? Yes? Okay, yeah. Okay, great.
So when elongation.
You can do that. That's the way to do it. So, Okay, so this is the this one is using this one there's one above it. What we say, all right. The displacement of what you're saying, displacement of this part plus the displacement of this.
or doesn't, I would say that's 90%. Right?
Oh, yeah. I did that much.
So that's fine. Right? And like remember, this is zero. What we don't know about these two. Right? We can't, we don't know that we like pick up differences. Okay, because it's actually extreme. Right? If you look at all this.
It was a long day. Thank you, Professor.
All right, have a good one until Thursday. All right. So it has zero, there's zero displacement, there's zero displacement. There's an excess. I take the bar, right? I put it here. This is the fixed L. This is the fixed L. And then I apply a force. I do apply a force, right? But look what's happening. You apply that force, you move, right? This and this will not move. But this and this and this and that. So, but we don't know how much that moves. We don't know how this moves to that. So this is. But if we use a force, some forces, in this case, then we would know how much we would know today. Okay, so then you can figure it out what's did you know that this place is zero of the t squared? You just typed it out. R2 and R1. This is still not enough. Okay. And this is where you do. This is certainly. So there's certainly this is right. So this force is acting. So it's like a body, and I've got these forces that are
Yes, like the eye crash. The eye crash. I'm gonna get the 15 minutes. I don't know, maybe like I'm the type of person to like keep my phone until I'm like literally like
this information. This information. So this is right. This is right. Okay, this is right. I don't know how you say this. There is no place you're the fact. But that's not what I don't find out your job to know those reactions unless you go. That's right, right here. That's right here. Right. Yeah, but when you know, how do you figure out what force to it? Or R2, or how do you figure out what force to it? It's not even a force, it's not even that.
Yeah, okay, so you have to.
And then I was like, I saw on Saturday,
I-
9 p.m. as well. Oh, yeah, no, I think you made the right choice. No, because I will not be going home that.
Hey, you're asking the question, this is very.
So I understand issues of rights.
Sure, what's up? Okay, yeah. Yes. So just to make it easier.
Yeah.
With external forces, you can put them however you like. You don't have to follow it eventually. Okay. For external, once you do internal sciences, we have to follow, or we should follow it. But that's just a thing. That's saying, all R2 going to R, or R1, whatever you want. So when you do the whole equilibrium, right, so this is fine, okay, oh, that's just, okay. I was like, so when you draw your diagram, okay, you wanna draw it such that you this is a little bit weird because I actually changed the order, it's at the very end, actually. Question 2, the answer is that.
Yeah.
This is the problem. So I accidentally, what happened is when I created, I didn't do it to be mean on purpose, but like, it ended up being out of order, and I haven't fixed it. But what I've tried to do is I've tried to put the questions in the slides, so we know when to answer that question, based on what I've done. No, they're not the same, because this is a statically indeterminate problem, alright? Like for this other problem, like before, yeah, it was nice, like, well, you could kind of, you could push it, but here's a statically indeterminate. Alright, have a good day, see you later. Thanks for coming. Sure. Okay, maybe I'll go ahead and stop the video. Since we're going over it. Okay.